Hello everyone. I'm very excited to share my work with everyone. I'm Guo Zhuoxiang from Institute of Computing Technology, Chinese Academy of Science. My title is Push the Limits of Supercritical Flame Simulation at Detailed Transport and Chemistry Accuracy with Deep Learning towards the training cell scales. First, let's start with background. As liquid rocket engine evolve, simulating supercritical combustion at ultra-high pressure becomes crucial. In the supercritical state, the clear boundary between gas and liquid phase disappear, forming a single phase. This leads to higher thermodynamic efficiency, more thrust, and greater payload. However, simulating supercritical combustion is challenging. The thin flame thickness under high pressure, requiring dense guard and smaller time step for flame simulation, which means demands more computational resource. This work used two supercomputers to perform flame simulation. The first one is Fukaku from Japan, and the second one is the New Shenwei supercomputer from China. Both of them are based on a many-core architecture. A key difference is that Shenwei feature a heterogeneous many-core design. Each CPU in Shenwei is divided into six groups, which with this group contain one master core and 64 slave cores. The master core is mainly used managing the slave core's communication and I/O operation, while the slave core provide substantial computational power. Moreover, each slave core in Shenwei has 256 kilobytes programmable local memory. High-speed communication between slave core is achieved through the RMA mechanism. The software we optimized is DeepFlame, developed by Professor Chen. DeepFlame use the neural network algorithm to replace complex calculations of mechanical source term and thermal physical properties in traditional flame simulations. Besides that, the other fluid dynamic parts utilize FE method from open form to solve the equation, which involve the constructing and solving of multi-sparse system. So here are our three targets. First, we need a efficient neural network inference module to compute the neural network algorithm in DeepFlame. Second, for fluid computation, we need to optimize the FE method in open form to suit many core architecture of supercomputer we use. Moreover, both Fugaku and Shenwei supercomputer have more than 100,000 nodes and requiring launch 600,000 process. Therefore, our program also needs robust scalability to further leverage the full machine performance of these supercomputer. Next, I will discuss the problem and the challenges for these three targets. First, the DNA inference. This is the ODE-net used in DeepFlame. In the initial version, the JLU active function was highly inefficient on both Fugaku and Shenwei, accounting for about 50% of the time in DNA inference. Additionally, use lower precision in DNA inference can enhance computational speed. In the fully connected layers, bias and the GLU operator can be fused to reduce memory access. In the FV method, we mainly face three problems: poor locality, indirect access, and write conflict during the sparse system construction, which pose significant challenge to multi-thread parallelism. For the long vector many-core architecture machine we use, there are crucial issues. These are crucial issues that must be addressed. Another issue we encountered in large-scale simulation is that the volume and the time of I/O increase linearly with the scale of simulation. This figure shows the results after we have made some optimization. In fact, the original version of OpenFOAM could only launch about 10,000 processes, whereas our foam machine simulation requiring launch 600,000 processes. So this is a summary of the challenge and our solution for this three parts. Next, I will provide a detailed introduction for our solution for each module. The first is DN inference module. We significantly improve the performance of matrix multiplication in DN inference by using mixed precision techniques. While staying within acceptable occurrence limits. On the right, you can see our occurrence test. Additionally, kernel fusion techniques is employed to fuse the matmul, bias, and the GLU operator into a single operation to reduce memory access. For GLU operator, its inefficiency mainly comes from the need to call the tangent edge function in its original implementation, which is mainly costly on Fugaku and Shenwei. We address this by approximate mixing the GLU function, thereby avoiding the use of expensive tangent edge function. Additionally, on Shenwei, the confidence table can be stored in local data memory of each core to further accelerate computation. Here is the result of our optimization. The DNA inference part has been accelerated by more than 8 times on both Fugaku and Shenwei. Next, let's discuss the optimization of FV method. To elevate the issue of poor locality, we first use the mesh renumbering method in OpenFOAM to rearrange the cell based on their central positions. This ensures that physical closer cell have closer cell ID, significantly improve the locality of sparse matrix. This slide shows the mesh and sparse matrix before and after mesh renumbering. In our example, after reordering, the sparse matrix become a multi-diagonal matrix, which provide more opportunity to for optimization. Next, we adjust the sparse matrix format used in sparse solver. The original LDU method in OpenFOAM has low parallel efficiency, making it difficult to leverage the performance of many-core architecture. It also poses challenge for vectorization and involve more indirect memory access. In our case, we use DIA formats in sparse matrix solving process. This format has a higher parallel efficiency and is easy to vectorization and no indirect access. This is important for Fugaku and Shenwei, since both of them feature 512-bit vectorization vector instruction. Additionally, We also accelerate the conversion of sparse matrix formats by pre-compute the mapping of non-zero elements. So to address the red conflict issue during the construction of sparse matrix, we implemented the mesh coloring method on Fugaku and mesh partitioning method on Shenwei. The mesh coloring method involves more memory access, which is suitable for Fugaku with its high bandwidth. In contrast, Shenwei has lower memory bandwidth, so we use mesh partitioning method effectively utilize the high bandwidth RMA mechanism of the Shenwei. Here are the results of our optimization. The construction and the solving process of sparse system are accelerated by 8 times over 8 times on Shenwei and Fugaku. Next is our optimization for startup IO part during the startup. The first problem we faced was that the block mesh and decompose program for generating and partitioning mesh could only run serially. Use them directly for 600,000 process is not feasible. Our solution is to first create a coarse mesh and then refine it to get a final mesh. Since the refinement can be done in parallel, another issue was the massive I/O data volume. Our estimates show that the data for refined 600,000 process mesh would be over 100 terabytes, which is unacceptable. To solve this, we come up with a multi-procedure fusion method and combine the refinement and the simulation process into one program. This reduces the I/O data volume from 100 terabytes to less than 12 gigabytes. Additionally, the collected format of OpenFOAM does not support parallel. We fixed this by building an index in advance and allowing multiple processes to read concurrently. In addition, we introduced a two-level parallel I/O method to balance the number of process reading at the same time and the amount of scatter communication. This shows the optimization effect of our two-level parallel I/O method on Fugaku, where I/O time has been significantly reduced. It's important to note that these results are after using the multi-procedure fusion method. Without it, a large-scale simulation would not be feasible. Okay, I have covered all our optimization method. Let's discuss the results of large-scale test. The first is the strong scaling. On New Shenwei, our simulation expand from 3,072 nodes to 98,304 nodes, achieve 13 times speed up. On Fugaku, it spanned from 4,608 nodes to 73,728, resulting in a 9.6 times acceleration. Next is weak scaling. On the New Shenwei, our largest simulation involves 618 billion cells with a float point performance reach 1.2 exaflops, which is 21% of the theoretical peak performance. On Fugaku, our largest simulation involved 154 billion cells with a float point performance reach 316 petaperformance flops, achieving 31% of the theoretical peak performance. Okay, finally, this is the summary of our work, including all the optimization and final results. Thank you for your listening, and here is my email. If you have any question, I'm very happy to discuss further.